Hello, good morning, everybody, or good evening, good afternoon. We are presenting this webinar on behalf of the Copernicus Climate Change Service, and we are going to present some of the activities under the Copernicus Climate Change Service Energy Operational Service. So that's C3S for short, Energy Operational Service. Today we're going to focus on seasonal forecast, and I'm going to give a short introduction, and then I'll pass over to the speakers as you saw in the announcement. So my name is Alberto Trocoli. I lead the Energy Operational Service. I'm the C3S, and I'm just going to tell you a bit about the overall aims of the project or contract and what we are achieving with this contract. So just a bit of background, this operational service started off from two preceding proof of concepts. One was called Clean for Energy, and the other one was European Climatic Energy Mixes, or ECM. And the merger of the two led to the team that is now building the Energy Operational Service. As you can see from the bottom, the activity started in May 2018, so over a year ago, and we are over halfway through the planned contract, which is for 2 years. This may continue as an operational service, but for now we're aiming to have the system delivered by the end of April 2020 in an operational manner, available publicly to everybody and for free. That's important attribution of the service. The policy of C3S, in fact, is to provide all the tools and data that are developed under the C3S or Copernicus more generally for free, so that people can develop their own tools or services and or just do their own analysis. The consortium behind the C3S Energy Operational Service is composed of 6 organizations led by the World Energy and Meteorology Council, with the CEA in France, Météo France in France, Électricité de France in France, Met Office UK, and Armin in France. So very strong team to build this service, which has its rationale, the development of a climate service with and for the energy sector stakeholders, which means that we are not just producing climate data and not just capacity factors, but we are looking at also energy variables. And we also have various activities to engage with stakeholders, one of which was held last week on the 26th of June in Denmark, alongside the International Conference Energy Meteorology, and there'll be some output from that. So I'll give the link for the web page where you can find information at the end of the webinar. We also aim to strengthen the knowledge of climate scientists so they can support the energy sector in a stronger way. The way in which the service is structured is along 3 streams. One is historical, so like measured variables, both for climate and energy, and this covers the period 79 to present, and is based on climate data from the reanalysis era 5. Then we have the second stream, which is the object of this webinar, a seasonal forecast, which eventually will cover 3 systems. At the moment, we are dealing with 2 systems, ECMWF and Météo France, 2 operational systems already available through the C3S. And the third stream is the projections. And at the moment, we are dealing just with Europe, and therefore we only take Eurocordex, but that can also be extended. In terms of climate indicators, we are looking at temperature, precipitation, solar radiation, wind speed, and mean sea level pressure, which are then converted into energy indicators to produce electricity demand, hydropower, both in terms of reservoir and run-of-river, solar power, only PV, and wind power on and offshore. We have quite a complex workflow diagram. This is just an illustration, but it's much more complex in practice. I won't go into the details, and you can get in touch with us if you'd like to know more. This will be documented also through the service when it becomes available by April 2020. Okay, so agenda for today. We have quite an elaborated agenda, but we've got some of the best people to present the seasonal forecast operations in general, and in our case for the C3S energy system. So we go through some basics first, and then what are the implications for the operational systems, and we'll also look at how the seasonal climate is converted into energy indicators, and then some demonstration and conclusions. We'll also have about 10-15 minutes for question and answer at the end, and we may continue if there is interest beyond the hour. And the webinar is recorded and will be available online. So I will now switch to the presenters and enjoy the webinar. Okay, if you would like to take over Christian first as a first presenter, the floor is yours. Thank you, Christian.
Thank you, Alberto. So this is Christian Biel from Meteo France. So yes, I will go to the first slide. Okay, so I will give you some basics about seasonal forecast. So seasonal forecast is often presented in a seamless context, like on this chart. So you can see that seasonal forecast is somewhere between weather forecast and climate projections. But the information contained in each kind of forecast is very different. For short-term forecast, forecasts give information about the chronology of meteorological events. So in a kind of movie, hour by hour or day by day of the different states, different weather conditions. Concerning seasonal forecast, long-range forecast in general, you don't have access to this level of detail. You don't have access to the chronology of the events. You have access, like it is written on this graph, to climate variability, internal variability of the climate. The print of this signal in opposition to noise is visible through statistics calculated on the different variables. So, for example, probabilities of circulation of scenarios, number of days below or above specific thresholds, for example. So this is one of the key points, something different from weather forecast to seasonal forecast. Another important point raised by this chart is about predictability. When you look at weather forecast, this kind of forecast relies on the knowledge of the initial conditions. This is essential to have good weather forecast, to have a good knowledge of initial conditions. When you go further in range, when you go to longer time scales, you have to rely on the boundary conditions, boundary between the atmosphere and the other components of the climate system. For example, the ocean states or the ground states, the soil wetness, for example. So because of the slow evolution of this other component of the climate systems, and because of the interaction between these components and the atmosphere, it brings some predictability at this seasonal scale. So this is the concept of forcing. So what are the forcings that could influence climate variability on Europe? You can see here on the chart summary of the main forcings that could influence European climate at seasonal scale. First of all, ENSO, which is El Niño Southern Oscillation. This is the main source of predictability at seasonal scale at global level, and it is known also to have an influence over Northern Atlantic and even over Europe. Of course, the influence is much weaker than over the Pacific or over North America. Anyway, we can have some predictability coming from ENSO over Europe. And closer to Europe, the Atlantic conditions, the stratosphere, the cryosphere are some other elements, some other boundary conditions that could influence the European climate, and especially the variability. But we have to say that the predictability, seasonal predictability over Europe is still modest compared to other parts of the world at the same latitude. Because we have to know that the climate over Europe is mainly driven by chaotic conditions. So this kind of forcings only partly influence the climate variability. If we look now at the source of information, source of data at seasonal scale, here you have some examples of web portals providing some products or data or information about seasonal forecast. So there are many centers over the world that operate models, global climate models, and give access to some seasonal forecast data in real time. And these models are in constant improvement, supported by active research projects. So this is an activity, this is a real-time activity. Anyway, this kind of product, this kind of model rarely feed applications over Europe. So one of the main goals of C3S is precisely to facilitate the use of seasonal forecast for applications. A key point in the development of applications is the access to data. So with C3S, you have access to data through the climate data store, and you have access for seasonal forecast to a set of 5 models. You have access to their past forecasts, the reforecast of the models, and the real-time forecast of climate indicators. Plus, thanks to this, the kind of sectoral projects like the energy project, you will have access to climate indicators at seasonal scale. But beyond data and product provision, there is a strong need of support from users for the data to become usable. So it's not enough to have skill. The real added value of seasonal forecast can be measured by the usability of this kind of information in the decision making process of end users. So this is another main goal of C3S, to facilitate the use of product by strong support to users, by communication, by interaction with end users, and of course by this kind of webinar.
Okay, so thank you, Christian. Hi everyone, my name is Lucas Gregis from Météo France, and I will develop a little bit on the seasonal operational stream. So, as both Christian and Alberto said, the C3S Energy is an operational services, and Météo France take care of on the seasonal forecast path. So we provide meteorological data, and we are also working with the energy sector to I'm sorry, just a pop-up. So we are working also with the energy sector for the energy models, and we are combining the two to provide our indicator, and we will make them available on the climate data store. And it is a main goal of this SIS to make some publicity on the climate data store, which is a new path to retrieve some historical, some seasonal, and some climate data. For example, if you are used to retrieve some reanalysis, such as ERA interim or ERA 5, and you used to do it on the Mars catalog, nowadays you'd better to do it with the climate data store. So when we are speaking of seasonal forecast, it is always about a large ensemble, because all the models are ensemble. The larger the ensemble are, and the better it is. So most of the seasonal forecast models have at least 50 members for forecast, and more than 25 hindcast, so reforecast member. I will develop more on the hindcast later in this presentation. And it is always fine to do some model intercomparison. So the diversity of the source is always something to keep in mind. So nowadays on the climate data store, we have 5 different seasonal forecast models. So the European Center one, Météo France one, the UKMO, the Italian model, and the DWD. So the German model is always already available. We will retrieve all the data on the climate data store to produce a proof of concept of so if an energy company want to do some products on seasonal forecast, it is a proof of concept. So we did something, and now it is you to play, you to do. The seasonal stream, the workflow is really complex, so I will not read it completely, but I will speak on the left part of this diagram. So we are retrieving the data, the raw data on the climate data store. Then we are doing some bias adjustment, which give us the climate indicator. After we may add some country aggregation, and after those climate data store, after those indicator, we will combine, we will add the energy data, but it is after the production of the climate indicator. And the skill assessment is also made afterwards. And after all those steps, it is uploaded on the virtual machine, on the public virtual machine, so on the climate data store. So for the moment, we are ready to make the data available from 2 seasonal models, so the European Center model, CIS5, and Météo France Arpège 6M6. As you can see, both of those models have 51 members in forecast and 21 members in hindcast. One hindcast is the operational model running on a past period. So it is initialized on ERA 5 reanalysis. A reanalysis is the best compromise that you can find between observation, physical observations that we know are wrong, and the models that we also know are wrong. So it is a numerical compromise, and it is the best that we can find. There is some differences between those 2 models. on the, for example, the resolution, for example, the parameterization of the convection, and also the way to initialize the members. For example, C5 initialize all its members in one single day. It is a burst approach, whereas Météo France initialize its member on 2 or 3 different days. It is a lagged initialization approach. Both those approaches have their pros and their drawbacks. And by fall 2019, we will also provide a GLOC5 indicator, which GLOC5 so is coming from Météo France, from Météo Office, and it is also a lagged forecast. So 2 members are initialized every day. So by the end of the month, we obtain around 62 members. So it is a good ensemble. The main difference here is that Météo Office release the model every month. So we have to recompute the climatology of the model every month. So that's why we will retrieve the hindcast every month. So technically, all our code are object-oriented Python 3. And in a way to promote the interoperability, it is only a free, libre, and open source library, and standards such as, for example, NumPy or even Python is a standard and open source. We try to keep the project the simpler, so with a minimum of a different class, and we separate the core of the process to the method used for example, quality assessment. So it is 2 different files. The treatment of the forecast is quite fast because it is never more than half a gigaoctet to treat. So within the next 6 hours of the release of the raw model, we can provide the indicator. Actually, the main limit here is that is the time to retrieve the raw forecast from the data. But after we have the data, it is quite fast. And at the end, we will provide some anomaly. For example, here it is the anomaly of this June 2019 for the period July, August, and September. So you can see that we forecast a quite hotter than usual signal on the most part of Europe. So I will let Raphael continue.
Yeah, so thank you, Luca. Christian introduced the basics on seasonal forecast, and Luca also talked about more the setup of the operational services. So now I'm going to talk more specifically on what you really going to see on the climate data store, and especially the description of all these indicators. It's going to be the climate indicators, so more close to the classical meteorological parameters, and also some indicators close to the energy sectors. So all of you may know this problem of all the energy sector, the demand and supply balance. So each of you are on one or several parts of this diagram. So you have the production of electricity on the side, you have the transportation and distribution with the TSO and DSO, and the consumption on the other end, and the market all everywhere. Basically, all those 4 activities do need meteorology as an input. Most of the time, it's temperature, precipitation, solar radiation, and wind. Basically, for consumption, you most of the time take only the temperature to forecast some consumption. Production, you could have wind or solar. It depends on wind turbine or photovoltaic. But definitely here you are using some post-processing model to convert meteorological parameters to energy usable variable. In this project, we are doing both actually. We are providing you the best seasonal forecast for meteorological parameters, but also for energy parameters. So it's going to be demand indicators, electricity demand. It's going to be also a wind production for onshore and offshore plants. It's going to be photovoltaic production and hydro, which include run-of-river and reservoir production. So actually, you could do both. You could do, on one hand, taking the meteorological parameters and apply your own model to have, for example, electricity demand. Or you could directly take the electricity demand, or you could do both and compare your result with ours. So a little bit more precisely on the climate indicators. So what is closer to meteorological classical parameters? So the 2-meter temperature, you get some 6-hourly basis forecast up to 7 months. It's instant value, so the temperature at a given time, and you have a gridded value, so on the whole domain with the 1 degree resolution, so approximately 100 kilometers, you're going to have this temperature forecasted, and you could compute some anomaly or whatever. The same for total precipitation. The differences is like here we are on a daily basis. We don't have all the time set during the day, and it's a daily amount of total precipitation. You also have the global horizontal regions, especially if you are doing some photovoltaic production forecast. Here again, you are on a daily basis, and at the end for the wind turbine, you can have the wind, 10-meter wind, but also the 100-meter wind is going to be given through C3S. For all those 4 indicators, we also give some net zero aggregation if you are using some national country scale model. You can use directly those data. So it was those meteorological parameters, and now in this project we're going to go a little bit further to your activities and provide some indicators really close to your activities. So electricity demand is going to be computed from temperature, solar radiation, wind, calendar data, whatever, and it's using a statistical model and the reference data to make the training are NSOE data. And it's a net zero aggregation, so you can have demand forecast only at country scales. You're going to have also onshore and offshore wind production. So it's actually taken from the 10-meter wind. So we're going up to 100 meters to go closer to the wind turbine. And after apply some widely used turbine curve. Those are mentioned here. So the 2 Vestas with a different capacity of production. And you have here a gridded value also at 1 degree resolution. The same for photovoltaic, actually. All the computation is taken from the paper of Sandrone et al. 2018. It's also gridded value all over the domain, so it's a big Europe. And you have here especially capacity factor of aggregated PV production is that for each pixel of the domain. And finally, the fourth one, so hydro production with a run-of-river and reservoir production. It's a country scale aggregation, also with a statistical model, which is actually not the same. And the reference is also the NSOE data. So all those models have already been presented in a previous webinar that you could find here in the link at the end of this slide. So as Luca already said, we will address 3 models during the project. So for the moment, we are only dealing with the ECMWF1 and the Météo France 1, and it's going to be for fall 2019, the Met-Office 1. You have several differences in the modeling for all those 3 models, but basically you have the quite same ensemble size. You have the same period of hindcast also. Just to notice that the raw data the model are run in different resolution at the very beginning before the climate data store. So we could notice that ECMWF is approximately 36 kilometer resolution. For the Météo France one, it's around 50 kilometers, so 0.5 degree. And for the Met Office, it's something like 60 kilometers for mid-latitude. All of them are of course, as Christian introduced, coupled with the ocean model, which are actually ocean and surface model, and all of them are different for each system. Here is like a summary, but also a table mentioned. Yeah, it's a summary of all what I said. So you could find temperature, precipitation, wind, solar radiation for the climate indicators, so close to the meteorological parameters, with all those three models, ECMWF, MF, and Met Office, with a resolution, temporal, and spatial resolution. And for the energy indicators, electricity demand, wind power, solar power, hydropower. Oh, something is missing here. But so I'm gonna talk more about it. So the idea here is we are computing indicators, so from each ensemble members and for each time step. But the idea is we are not going to give you all the ensemble members, so all these 51 ensemble member. We are giving you some probabilistic forecast, so it's going to be a mean anomaly, but also probability of lower, medium, and higher terciles. We are also supposed to give some assessment scores. So it's going to be correlation with error 5 anomaly, but also ROC score, which is going to give a more probabilistic score. And Luca is going to introduce those indicators after. So just to finish this part, I really want to highlight once again that all those data are given to you with a actually very small time scale and resolution, but you definitely have to handle this like climate variable. So you're gonna apply maybe your model, posterior model, but after you're gonna have to make some averages, time averages over 1 month or more, but also you could have some averages over a spatial region. I'll let Lucas continue with the indicator assessment.
Okay, thank you. Let's speak about the assessment of the data. First, we have to take care of the bias. And to address this issue, commonly with seasonal forecast, we do some hindcast. So as I said before, hindcast is the operational model running on a past period. So it gives us a model climatology, and with this climatology we can do some tercile, we can do some probabilities, we can do some threshold, and so we can do some statistics which are essential with ensemble data. The reference that we chose is ERA 5 at a 1 degree resolution. And the climatology period is also important. It is a 24 years of hindcast and climatology period, so 1993 to 2016. With 1993 is an important milestone because it is the start of the assimilation of the satellite altimetry value. So it is a major improvement in the reanalysis. And although 24 years is quite good because the climate is changing, so we cannot go too far in the past because it will be a different climatology. So in seasonal forecasts, the most common way to biased adjust a data is to do quantile mapping. Quantile mapping is simple and quite straightforward actually, because we do trust that the reference is true. So we are fitting the raw data in the reference distribution. So we are ranking the data and taking their centile, for example, and the bias adjusted value is the same centile but taken in the reference distribution, and we do some linear interpolation between the centile, but for the extreme value we do not invent some new extreme. So for example, if we forecast a very hot value and an extreme, we do some linear extrapolation with the two last centile, but we limit the value obtained by the most extreme value taken into the climatology. It is the months around the date. So it is a limitation of contact mapping because, for example, the hotter value tend to be more common with the climate change, and the colder value are also more rare. So it is something to keep in mind with contact mapping. To give an example in practice, on one grid point near Berlin, on the parameter temperature, you've got two plots, so one plus 1 month ahead, and the other one on the right, it is 3 months ahead. You can see that in black, the raw data are affected by a cold bias, and after content mapping, you can see that the blue, so it is the bias adjusted hindcast, and the reference ERA5 share barely the same distribution. And you can also see that the extreme of the two distribution are similar. So with this simple visual verification, it seems that content mapping went okay. I show this map only to put the stress on why you should do some bias adjustment with seasonal forecast. As you can see, the bias is very strong. It is commonly for temperature more than plus or minus 4 degrees, and with peaks up to 6 or minus 6. And something to keep in mind also is that the bias varies from one location to another, but it also varies from one day to another. So for example, here it is on June, and it is for the months of July to September. But if I take some, even the same run of June, but for the period maybe October to December, the pattern of the bias on the mean error will be completely different, or maybe completely different. Another thing that happens here is that the bias tend to be higher on the continent and slightly reduced on the ocean because, as Laurent said, as Christian said, the oceans are inertial mass, so they are more easy to forecast. After bias adjustment, I'm sorry, the colors are the same, but look at the scale; it is completely different. After bias adjustment, the peaks are less than a half a degree, minus half or plus half a degree. And you can also see that the pattern changed. So we choose some points of interest in Europe. So here it is 17 points, sorry. It is just to verify that the physics of the signal has some sense. So in this presentation, I will just show two plots. So one in the middle of North Sea and on the oceans, and one good continental point near Budapest. So on this plot, on the top you can see the mean error, and at the bottom the two plots are the erimecy, and it is for the point of North Sea. The two left diagrams are for winter period, so it is initialized on January, and for the 3 months of February to April. And on the right, it is in August, initialization on August, and for the period of September to November. You can see here that the bias differs in the time. In winter, we have a cold bias, and in summer, it is less obvious to conclude. You can see that the patterns are different. Take a note of this of the value of the bias. It is nearby -1 degree in winter. And on the next slide that I'm going to show now for Budapest, you can see that the bias is much stronger. So it is more than -2.5 or maybe even 3 degrees. You can also see here that the pattern change in the temporal way. So we are onshore, so more interannual variability, less predictable, so the bias tend to be higher also. So that was for temperature. And now if we look at the wind parameter, here it is only the mean error. On the top it is the North Sea, and on the bottom it is Budapest. You can see that for the wind, the mean error is higher on the ocean, which is not surprising because the value, the mean value are higher. And you can also see that the bias adjustment seems to be better in the continental region, but it may be due to the quality of the reference data. But in general, for the wind, we expect some better bias adjustment. So the point, the diagram that I show are made on a step-by-step basis. Sorry, and we have now to develop some statistics to take in account the average on 3 months, because I will show the next plot now. You can see that on a step-by-step basis, the signal, the scale is very, very low. This is an anomaly correlation, but it is a correlation, the temporal correlation. And which it is basically, we forecast a hot value, and if we observe a hot value, we are correlating readings, it is fine. So this scale score is varies from -1, which is total anti-correlation, to +1, which is perfect correlation, and 0 means no signal. So as you can see, when you consider some step-by-step value, you have only noise, very poor signals. The early part of this plot is demonstrate the period where the seasonal models is sensitive to the initial condition. You can see that after 50 steps, and steps here for temperature is 6 hours, so it is 15 days. After this, we have no signal. Before, it is a kind of deterministic signal. So that's why we will provide, also on the next plot I will show you, we will provide some quarterly, so it is 3 months skills, and on a 3 months basis, the skills appears. But as Christian said, we are quite far away from the main forcing. So you can see that near the Eastern Pacific, we have a good correlation ranging from 0.8 to 1, so it is good. And all the cryosphere in the north seems to be better. But in middle latitude, we are near from 0, so the skills are poor. But still, there is a little signal that may be useful for an important energy provider. Yeah, and always, as I said before, if you look for another skill, so for example, if you take the run of August and the lead time December, January, February, it will be different. The pattern may be different. We will do the same for the ECMWF data. And so this is a map provided by the ECMWF Center. So always a good predictability in the tropics, and quite poor predictability in our mid-latitude. So just to be fast on the hindcast prediction process, it is an heavy task. It is always done in Python, always object-oriented, as I said before. It is heavy to proceed, but actually not that heavy. It is long, so it is a week to compute all these hindcasts, and it maybe take time to retrieve the data. But note that we do the computation with a 64 gigabyte of RAM on our machine. So in the near future, it will be possible to compute this kind of computation on a good desktop computer. So, okay, heavy for the moment, but not that much actually. Unfortunately, the hindcasts are computed once for all. So we retrieve the data, we do the bias adjustment, and then we retrieve only forecast in an operational chain. So that is possible for ECMWF 6.5 and for Météo France ARPEGE SM6, but as I said, not for ECMWF 6.5. So maybe the upload and the data will be released slightly after the two other center. So I will let Raphael to conclude.
Yes, definitely. So here we're going to try to conclude a little bit, but just before, to show you some example of indicators you could find on the climate data source. So it's NetCDF file and also CSV file for the country aggregation. And here it's some graph we are doing from those NetCDF file. So here is just example of temperature on the left side and precipitation on the right side. It's anomaly for July, August, and September with initialization on June. So it's forecast for this summer. So what we see just very quickly, so hot anomaly all over Europe for yes, 0.5 degree at least. And for the precipitation, we are kind of a decrease of precipitation, so a negative anomaly here observed over Europe. So here, once again, it's all the bias corrected forecast. So this was for the climate outputs, so meteorological data parameters, and here it's for energy indicators. So we're gonna just have here photovoltaic production anomaly on the left side. On the middle one, it's offshore wind production, and on the right side, the onshore wind. Also, all those graphs for this summer. So we see a kind of a positive anomaly for the photovoltaic production and a small positive anomaly for the onshore wind. So this was just example. Of course, you could do your own graph with all the data. You will actually, and you just have to do the graph the more useful for your activities. So just to conclude, maybe a little bit more widely for all the projects. So the C3S is going to give you some energy indicators. So we have addressing some meteorological parameter close to your activity, so temperature, precipitation, solar radiation, and water and wind, but also electricity demand, solar production, wind production, and hydro production. It's gonna take reference to ERA 5 for all the product. So 3 time scale are covered. Here we were only talking about seasonal forecast, so in the middle. But you had also some historical data set. A webinar was made on the 22nd of May this year. And there is also some climate projection, which are going to be introduced and explained on a webinar the 12th of September this year. And for all those 4 times stream, you're going to have some electricity demand, wind power production, once again, photovoltaic production, hydro. And for the seasonal, you have here the time step and resolution for all those data. So all of this is freely available once again on the Climate Data Store, or will be soon. And also the code, I guess, is going to be available too, the Python code, if you want to take it and use it by yourself. For some future plan for the short term, so till the end of the project, set operational the real-time services for the ECMWF Météo France model, but also for the UKM Lucifer seasonal system. And of course, we release the whole documentation with all this assessment information, very important for you to take decision. And for longer term, it actually depends on you, users, what maybe you need for future projects. So it could be a larger domain, other energy indicators. The idea of testing some other statistical adjustment, or any other things that could be useful for the energy sector. So thank you very much for your attention. Of course, feel free to send us an email. It could be here in Météo France or service energy@meteo.fr, but also to Alberto. The email is also here. And thank you very much.
Excellent. Thank you very much, Météo France team, with Christian, Luca, and Raphael, for this excellent overview of the seasonal forecast work under the C3S energy system, operational system. Unfortunately, we didn't hear from Sophie Martinoni, who is behind also this activity and is providing strong leadership at Météo France. So thanks for the work anyway. And now we have time for some questions. So we received some questions. If you want to continue sending other questions, please do so. We are going to show the questions now online, and the presenters will address them one by one. So I'm going to show them to you, and the presenters are seeing the questions, and so we could try to start with the first one. So the first one is, I'm working, well, I'll bring it up, I'll read it.
Yeah, it's about if we are computing the indicators, so we are doing it on net zero, so country scale. Are we doing it for the other scale, so a more regional one? During this project, it's not going to be for the seasonal stream. It's going to be, I think, for the other stream, but not for seasonal. So for this project, we're going to keep to net zero.
Okay, yeah, thanks. Can I also add that in addition to what Raphael said, that we are providing the 1 degree by 1 degree resolution, so people could in principle compute the NAS1 or other averages, but the idea is that we won't provide it mainly because we think there's not much skill in those smaller regions, and therefore it's a little risky exercise at this stage. But we do provide NAS2 for the other 2 streams, for the historical period and for the projection period. So if we can address the second question, please. So could you shed some light on the difference between wind speed? Yeah.
The difference is that for wind speed, it is a 10-meter wind speed. So we take the 2 on the climate disaster. We have the zonal and the meridian component. We merge them and we have the wind power. And for we have the wind speed. And for the wind power, we take the same total wind at 10 meter high, then we extrapolate it on 100 meter, and with those values, we apply I think we apply 2 power curves. One onshore, which is a Vesta, and it is a 3,400 megawatt kilowatt, and we have another power curve for offshore, which is 8,000 kilowatt. And for the next question, the practical question, actually I don't know. It is not in my hand to release the code.
Sorry, Luca, could we clarify? So the question is whether where we can find the Python code that you mentioned.
For the moment, it is only on the virtual machine, but actually we did not discuss yet how we will release the code. We will release the code certainly, but how will it be available for the public? Actually, I don't know yet. But it will be, maybe a GitHub or something like that.
Yeah, thank you, Luca. So just to add, and just to remind the audience that the timeline is such that the overall system will be available by the end of April 2020. With some intermediate steps, we may try to provide the code earlier than that, but that's our target. Of course, we can interact also offline and see whether we can collaborate on some aspects or provide some parts of the code if there is a specific question that you would like to address. The last question was similar. But actually to show whether asking whether we also, provide some tutorial. So yeah, that's a very good suggestion. So we may also look into that. We have already a program for a few webinars to come, but we could add this on Python as an additional one. So thanks for the suggestion. We actually have a request for a clarification about the difference between wind speed and wind power. So Anya Victorine is asking to have a bit state the difference between these two more clearly if possible, please. Either Luca or Raphael.
We may don't understand what the precision the person need.
Okay, so yeah, I also I'm not entirely sure. So maybe if we could provide, Anya, if you can provide a bit more,
the speed is
detail. Sorry.
The wind speed is in meter by second, and the power is in megawatt or kilowatt, or even in a capacity factor. So it will be the maximum possible production divided, the production divided by the maximum production possible with the turbine.
Okay, yeah, no, that's good. I think also we can refer to, as you said before, Raphael, we also have the previous webinars recorded and available online, particularly the one on energy, and I'll provide the link again here in the next slide. But I just wanted to mention the upcoming webinars. So thank you again for the questions. You may continue to send them offline, but we're wrapping up now, and just give you an indication of the next webinar, which has been fixed now for the 12th of September, and we'll send the announcement soon. This is about the third stream in our service, which is projections, climate projections for now, with a little discussion also on energy indicators, but mainly on climate for now. And then the following one is going to be in November 2019 on case studies. So basically, we are going to provide more detail to what we provided last week in the workshop I mentioned that ran on 26th of June. And then we will also run others to show how the service is coming up, also from a visual perspective, but we will provide these dates later on. But we intend to run one webinar every 2 months, then as we've done for the last 2 and 3 with this one. To conclude, I'd just like to show you where you can find the recordings and where you can find the additional information about the C3S energy service. So these are the links. On top, you'll find the recordings for this webinar when it comes available, the previous one, and several more, also from the previous C3S service energy, ECM, and the link below is more general information about the service. So I'd like to thank again the speakers for their excellent presentations, and all of you who attended this webinars, and also people who will listen to us on the recording later on. Thank you very much. Have a good day or evening and weekend. Bye-bye now. Okay, thank you very much, Christian, Raphael. I had to dismiss all the attendees, so that only us is
yeah. How many attendees were there?
About 30. We can send you we will get the statistics, and yeah, about 30, which is normal. We had about 70 75 registered, and it's always the statistic is pretty stable. It's about half of the people who register would then attend, and then there's also some statistics about how people follow the webinar. There's just one number. It was about between 40 and 60%, which is normal. So it's
okay.
Yeah.
30 at the beginning or at the end?
But yeah, 30 all the way. But we in the statistics we from the webinar, the GoToWebinar, we'll get also the timing when people joined and when they left and all the rest, so we can share that.
Okay.
We will send some emails to the people who left before.